All right, so let's get going on today's class. So what we're going to do today, now that we have taken a look at Chapter 8, Chapter 9, now that we've taken a look at the three t-tests, we're going to take a look at how an application of those tests, which is using them to make confidence intervals. So confidence intervals are oftentimes used not in an experimental setting, so not in a sort of research psychology setting, but oftentimes in an application setting, confidence intervals become very important. So we'll set this up with a few hypothetical examples. So let's say that you graduate from IUSB and you're a psychologist, and you get a call from the monkey sanctuary. You get a call from a wildlife sanctuary that takes care of chimpanzees, takes care of monkeys, and they call you up and they say, you know what, we've had an epidemic here. There's been an outbreak of a virus. We've had to quarantine the older monkeys from the younger monkeys. So we have a whole bunch of baby monkeys that have no access to their parents, a whole bunch of lonely baby monkeys, and they want to make sure that these baby monkeys are getting some of the attention that they need. And they heard about Harlow's experiments on the wire mesh mother and the cloth mother, and they want to know how many of these monkeys do they need to buy, how many of these surrogate monkeys should they acquire for their baby monkeys, because they are in the real world. They're working on a budget. They might not be able to buy a surrogate monkey for every single baby monkey there. So they want to know how many hours per day will a baby monkey spend with this surrogate terry cloth mother so that they can use their budget appropriately. So notice that this is a different question than what Harlow was asking. For Harlow and his studies, all he wanted to know was, do they spend more time with the terry cloth mother? And he couldn't really care if they spent 17 hours, 16 hours, however many hours. All he wanted to know is there a difference? Do they spend more time with the terry cloth mother? Sometimes, though, in the real world, you need to know how much more. How long do they spend with the terry cloth mother? And we're going to see today a confidence interval is one way to get at that information. All right, give you another example. Let's say that you are called as the expert witness, expert testimony giver in a court case that involves potentially vehicular manslaughter. And let's say that you are brought in because a lawyer, when they were interviewing or questioning one of the witnesses, did not ask how fast was the car traveling. Rather, they led the witness and they said, how fast was the car traveling when it violently and egregiously smashed into the truck? All right, so let's say that they asked this question and the defense lawyer objects and says, objection, Your Honor, they're leading the witness. And the judge knows that the damage has been done. The judge knows that the question has been asked, the memory has been rewritten. So now they want to know when this witness gives their testimony, how much did they overestimate their testimony? So they remember Loftus and Palmer and their studies on eyewitness memory, and they call you in, and notice that they are going to ask you again a very different question than what a researcher would want to know. A researcher would just want to know, is there a difference between the smash two and the hit group? But in this case, somebody's life may be hanging in the balance. Somebody's decision might hang in the balance by how much of an overestimation did this eyewitness have. Is it only 10 miles an hour? Is the overestimation 40 miles an hour? How much of an overestimation would this individual give? Because that's going to determine whether this person is guilty of vehicular manslaughter. So once again, for Loftus and Palmer, good enough for research purposes to detect that there is a difference. However, oftentimes in the real world setting, we need to know how much of a difference is there. We need some sort of estimate of the size of this effect. All right, and one last example. Let's say that you graduate here and you become an organizational psychologist, an industrial organizational psychologist, looking at how people work together, for example, in a large corporation. And let's say that one of these large corporations hears of your work and calls you in and says that they read about research on timeout procedures. And they read about how timeout procedures work for children, but they also work for adults. And we know as scientists that the 10-second condition was better, higher accuracy than the 5-second timeout condition. However, for these individuals, they need to know how much better, because redoing their workforce, redoing their computers, installing these programs to give their workers timeout periods if they make errors, that's going to be expensive. So they're going to know, they're going to need to determine what kind of an increase in accuracy can they expect to go with the 5-second versus 10-second condition. They need to crunch the numbers. So once again, for us as research psychologists, it's enough that there is a difference, right? That's theoretically interesting. But sometimes in the real world, we don't need to know just that there is a difference. We need to know how big is that difference. What is the increase in accuracy that we can expect? And that's what we're going to be working on today when we take a look at confidence intervals. So we're going to start today with an overview of confidence intervals. What are they? How do you do them? General principles about estimation. And then what we're going to do is we're going to apply it. We're going to go through one example of confidence intervals and how to do it with SPSS, how to use the simple single sample t-statistic to do a confidence interval. And then next time we're going to wrap up our look at confidence intervals by taking a look at independent means and dependent means confidence intervals. All right, overview of confidence intervals. Confidence intervals, they're still in inferential statistics, but this is an example of estimation. So we've been doing inferential statistics hypothesis testing. Now we're going to take a look at inferential statistics estimation. And this is where you use a sample statistic to stand in for a population parameter. You're interested about something in the population parameter, but all you have access to is a sample statistic. So that's what we're going to be doing with confidence intervals. They're a procedure for estimation. And a confidence interval is made up of two portions, two kind of concepts. And those concepts are the point estimate and the interval estimate. So a confidence interval is a combination of a point estimate and an interval estimate. So what are these two things? Well, a point estimate, that is a single number that you use to estimate some unknown quantity. So a point estimate is what we usually do when people ask us to estimate something, right? It's what we usually do when people say, how much of this? You know, you don't have the right answer, but you estimate it. So let's say that you were judging the height of somebody. Let's say that somebody was asking you, about a woman that you saw, and they asked you, how tall was that woman? Let's say that you were an eyewitness, to some crime. And they asked you, the police are asking you, how tall was the woman in question? You would usually at that point give a point estimate. You would usually say, well, she was 5'6", right? That's my estimate. This individual was 5'6". So that's a point estimate because you're giving a single number. One number, 5'6", that's your best guess. That's a point estimate. The other kind of estimate that you can give is an interval estimate. And an interval estimate is where you use a range of values in order to estimate a particular unknown quantity. So an example of a range estimate that would answer that exact same question, if they ask you how tall was the woman, you might say, well, she was between 5'2" and 5'10". So again, it's an unknown quantity, but this time you're giving a range rather than just a single point. So that's an interval estimate. You give a range of values. So these two estimates, they have trade-offs. So a point estimate has very, very high precision, right? You know exactly what you're estimating. You give an exact answer. 5'6" is an exact point. It's very precise. That's a point estimate. On the other hand, an interval estimate has very low precision, right? It's very imprecise. It's somewhere in that range. It could be any of a number of different values. 5'2", 5'3", 5'3½", 5'4". It could be any of those. It's very, very low precision. So point estimate, high precision. Interval estimate, low precision. But precision has a cost. You don't get precision for free. And the cost of precision is confidence. So point estimates, whereas they have high precision, they have very, very low confidence. So for example, if that police officer asked you, how tall was the woman? And you say, oh, she was 5'6". And they go, are you very confident that she was 5'6"? You might say, yeah, I'm pretty confident that she's 5'6". And if they ask you, are you confident that she's not 5'7"? You'd be like, well, no, I mean, she could be 5'7". I'm not confident that she's, exactly 5'6". If they ask you, are you sure she's not 5'6.5"? You'd be like, no, I'm not sure at all that she's not 5'6.5". 5'6" is my best guess, but I have no confidence that I'm actually correct, because she could be just 5'6.5", and you would be wrong, right? So high precision, low confidence, the two of those go together. On the other hand, the interval estimate, you have low precision, but you have very high confidence. So when that police officer said, you say she's between 5'2" and 5'10", are you confident? You'd be like, yes. Are you very confident? You'd be like, yeah, I'm really confident she's between those two values. Are you really, really confident? You'd be like, yeah, absolutely, I'm super confident that she's between those two values. And they can then ask you, are you really, really, really confident? And you might say, well, for that interval, no, I'm not really, 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 really confident. If you want me to be really, 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 really confident, then I'll say she was somewhere between 4'6" and 6'4", right? I'm expanding my interval. Now I'm really, 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 really confident. And if that police officer kept following his line of questioning and said, are you really, 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 super, really, really, really confident? You'd be like, well, no. If you want that level of confidence, she's somewhere between 3 feet tall and 7 feet tall. Now I'm really, 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 super, really, really, really confident. And if they then ask you again, are you absolutely 100% cannot be wrong? No way in, no chance that she's outside of that range. Are you that confident? You might say, no, I'm not that confident with this range. Let me make it a little bit bigger. I'm absolutely, totally, 100%, massively can't get any more confident that she is somewhere between 6 inches tall and 14.5 feet tall. Within that range, I guarantee you that that woman was within that range. So we can see that we're kind of talking about confidence rather loosely, but it's related to the size of the interval. The bigger your interval, the more confident you are that your estimation is correct. The more confident you are that the actual value falls within that interval. And we're going to see how we can use the t-test that we've been doing to actually not just talk loosely about confidence, like are you really confident? Yes. Are you really, really confident? Yes. Are you really, really, really confident? No. Not loosely like that, but to actually give a specified level of confidence. Actually create a confidence interval where we can say I am 90% confident or I am 95% confident, or you can give an exact confidence level for your estimation. All right. I'll give you another example of a confidence interval. I am about 90% sure that my voice is going to give out somewhere between 20 and 30 minutes into this class. So we'll see how far we can get with the vocal cords I got left. All right. So logic of hypothesis testing. Confidence intervals, they tie in to hypothesis testing. And they're basically kind of the next step that you oftentimes do in a hypothesis test. So for example, if we did a hypothesis test and we wanted to know what's the probability that our sample came from our population by comparing it to that comparison distribution, if we find that we're rejecting the null hypothesis, if we find that our sample no longer belongs to the original population, well then oftentimes the next question is, well, what's the population that it does belong to, right? Let's try to estimate what that unknown quantity is. Let's try to estimate what that unknown mean is of this treated population, because we have this treated sample. We know it doesn't belong to the original population, it belongs to the treated population. So what we basically do is we basically take that unknown treated population and figure out a new distribution of sample means. And we want to know where does our sample, or we try to estimate that population, but what we don't know is where our sample comes from in that distribution of sample means. Because maybe our sample comes from right in the center of that distribution of sample means. Maybe our sample comes from an edge of that distribution of sample means. Maybe our sample actually went into the tail of that distribution of sample means for that treated population. So we don't know how close our sample is to that sample mean, right? Sorry, to that population mean. We don't know how close our sample mean is to being a good estimator for that treated population mean, that new parameter that we want to know. However, we do know a few things. So let's take a look at the distribution of sample means from the treated population, right? This is what we're trying to estimate. What is the mean of this new treated population? So we're going to zoom in on this. I'm going to spread it out just so we can visually see this. So that's the mean of your comparison distribution. That's your treated population mean. You've treated your sample, you've changed it, it belongs to a new population. That's the mean that you want to figure out. And any estimate that contains this line, contains that mean, that's a successful estimate. All right, so any estimate that contains that line is going to contain that mean, that's a successful estimate. It's as if this line is 5'6", the woman's actual height. Anything that contains this line, like 5'4" to 5'8", that's going to be a successful estimate. So let's first take a look at a point estimate. There's your point estimate right there. If your point estimate has it has high precision, you could get lucky and your point estimate might be on that mean. But let's take a look at what happens when we combine that point estimate with a specific interval. And the interval is the width of the body of the comparison distribution. All right, so we are making the interval around our point estimate the width of the body of the comparison distribution. So we got the body, we got two tails. We're making our estimate the width of the body of the comparison distribution. Let's take a look at what an interval this wide will do for us. So if our sample mean actually hits the population mean that we're trying to estimate, we just got lucky. Our sample mean actually equals the population mean. Notice that within that interval, it contains the population mean. That interval is a successful estimation. It contains the population mean. Look at that point estimate right there. That point estimate got it wrong. Does not contain the mean. So this would be an example of a point estimate that did not successfully estimate the population parameter. It overestimated the population parameter. But notice when we put that width of that interval, when we put that body-wide interval around that point estimate, notice that the mean is actually in that interval. All right, so even if we're a little bit above, the interval still contains the mean. It's still a successful estimation. If our sample mean underestimated the population mean, once again, point estimate missed, right? Unsuccessful estimation. But once again, put an interval that's as wide as the body of your comparison distribution, and the population mean is in that interval. So another successful estimation. And what we find is that there are many, many means, many possible sample means that still with this interval have that successful estimation. They successfully estimate the population mean. So we have that interval successfully estimates the population mean. That interval successfully estimates the population mean. That interval successfully estimates the population mean, because in each interval, that population mean is within the interval. This estimation, this interval estimates the population mean. So does this one. So does this one. So does this one. So does this one. So does this one over here. All right? That's the first one that does not estimate successfully the population mean, because now the population mean is not inside the interval. And notice that this only happened when the sample that we were working with happened to come from the tail of the distribution. And that's the key to a confidence interval, because the chance that we're going to get a sample in the tail is equal to the size of the tails, right? The chance that we're going to get a sample from the tail is equal to the size of the tail, because this is a distribution of the sample means. Every mean from this population, every sample mean from this population is somewhere in that distribution. And it's only when we have a sample mean that comes from the tail that we miss the population mean. And the chances of that occurring are the same as the size of your tails. So if you have a tail, if you have two tails, and they are 5% of your distribution, right? There's 5% in the tails. What that means is that you have a 5% chance that you have a sample here that came from the tails. You have a 5% chance that your interval is going to miss the population mean. So you have a 5% chance of being wrong. What that means is that you have a 95% chance of being right. And that means that this is a 95% confidence interval. You can be 95% confident that you are going to correctly estimate this particular population mean. Let's say that you put 10% into the tails, right? If there's 10% in the tails, then you have a 10% chance of ending up with a sample that came from the tails. That means that you got a 10% chance of missing the population parameter with your estimate. So you got a 10% chance of being wrong. That means you got a 90% chance of estimating it correctly. So now you can be 90% confident that you're going to estimate it correctly. So this is how we control for the confidence interval. We control the confidence interval by controlling the size of the tails, and that controls the size of the body. And it's the size of the body that determines how confident we are, because again, the only way we're going to miss is when our when our sample mean just happened to come from the tails. And again, we don't know where the sample mean is coming from, but this is the only way that we're going to miss. All right, so that's the basic idea. Let's delve into this a little bit further. So where does this confidence interval come from? Why is it tied to a t-test? Well, it's tied to a t-test because this is the general formula for a t-statistic. You got your sample mean minus your population mean divided by your estimated standard error. That's kind of the general way that you figure out a t-statistic. We haven't seen that equation for so long because SPSS has been doing this for us. But it's a good idea to peek behind the curtain and see exactly where this comes from. So we have, if we want to solve for the population mean, right? Look, right there, population mean. That's what we want to estimate. So if we solve for that, just using algebra, we can get it down to the population mean equals the sample mean minus t times your t-statistic times the estimated standard error. That equals your population mean. That means your population mean equals your sample mean plus or minus, because your t-statistic goes on both sides, t times the estimated standard error. That is the formula for a confidence interval. So that gives you each piece of your confidence interval. So if we take a look at an individual confidence interval here, we want to estimate the population mean. That's that parameter right there. That's the value right there. That is going to equal your sample mean. Your sample mean is always your best guess. It's always your point estimate. It's always the center of your confidence interval. So if we could only give one number to predict or to estimate what the population mean is, it would be your sample mean. Your sample came from the population. You take your sample mean. That is your best guess. So remember that. That's the center of your confidence interval for any situation. So that's the sample mean right there. And then this plus or minus your t-statistic times your estimated standard error. That's what determines the length of your arms on your interval. That's what determines the width of your interval. So plus t times estimated standard error is one side, minus t times the estimated standard error is the other side of your interval. So we have our population mean equals our sample mean plus or minus t, our t-statistic, multiplied by our estimated standard error. And incidentally, that t-statistic is determined, if you're going to do this by hand, by looking it up in your t distribution table. So that's a t-statistic associated with tails that are that big. And again, you choose the size of the tails that you want. All right, so just to put some numbers on this, let's say that the mean, sample mean that we had, or the mean that we were trying to, the sample mean that we had was 100. The t-statistic times the estimated standard error turned out to be 11.5. This would put an interval of 100 plus or minus 11.5. So that's the size of the interval, because in this comparison distribution, the mean is 100, and those cutoff scores, in terms of raw scores, are 111.5 and 88.5, so plus or minus 111. And again, notice that if your sample mean is 100, you've gotten lucky, you've estimated your population mean, but if you build that confidence interval around it to the size of the body of your comparison distribution, then it doesn't matter if you overestimate or underestimate your confidence interval, so long as your overestimation or underestimation does not put you into the tails. So again, the only way you're going to miss with your interval is if your sample comes from the tails. Either side will work, but that's the only way you're going to miss either of your intervals. That's the only way it's going to break down so that you don't have a correct estimation. All right, so that's the overview of confidence intervals. Any questions on that so far? Okay, so what we're going to do right now is we're going to go through a calculation of a confidence interval. So we're going to use SPSS to do this, and you're going to find out that you've actually been calculating confidence intervals this whole time. So if you haven't already, go into Canvas, open up the Excel practice sheet, 28 practice, April 11th, confidence intervals, and we are going to start with the single sample confidence intervals. We're within that 20-minute mark. But this is the data that you're looking for. So we need that terry cloth data. You might have it in a previous Excel sheet as well. But this is the terry cloth data that we need in order to run our confidence interval. So once again, just kind of set up the situation. In this case, we got Harlow and his monkeys. For him, enough to know that there is a difference. But if you're in that monkey sanctuary and you have to buy surrogate mothers for these infant monkeys who needed to be placed in quarantine, and you don't have an unlimited budget, right? You got to spend money on food. You need medicine. You need, caretakers. You just can't be blowing the budget on a terry cloth mother for every monkey. So you want to know, what's the minimum I can go with to be sure that they have enough access to these mothers. All right, so we've already read through this a few times, so I won't go through it exactly again, but just to jog your memory, two types of mothers, terry cloth mother and the wire mesh mother. On average, they spend a total of 18 hours clinging to one of the mothers. If there was no preference between the two, you'd expect 9 hours for each of the mothers. A typical monkey spent around 15 hours a day with the terry cloth mother, indicating a strong preference for the soft, cuddly mother. We wanted to know, is there a significant difference? That's what a researcher would want to know. Is there a preference for the terry cloth versus the wire mesh mother? We found out that we've seen it already. Yes, there is a preference. That was statistically significant. The next question you might ask, though, is how many hours per day do these monkeys spend with the terry cloth mother? How many hours a day do the population of monkeys, now that we found from our sample that the population of monkeys prefers the terry cloth mother, the next question is, on average, how many hours per day does that population spend with the terry cloth mother? So what we're going to do is we're going to compute a 95% confidence interval, we're going to compute an 80% confidence interval, and lastly, a 99% confidence interval And we're going to do this with SPSS. So if you've already opened SPSS, feel free to set this up. Set it up to the point where we're ready to run the one sample t-test. So let me just get SPSS going here. All right, so we're going to set up this one sample t-statistic. So you can go ahead and do that. So we got the terry cloth mother here. Better be open there. Try that again. All right, we'll call this Terry. Data view. All right, and what we're going to do is I'm going to do this kind of two ways just to show you some of the things that you need to think about. All right, so I'm going to do it one way first, and then I'll show you the different ways. So when we're setting this up, we go to analyze. We go to analyze, compare means. It's the one sample t-test. Test variables is terry cloth. And remember that when we did the original t-test, we were comparing these hours that the monkey spent with the terry cloth mother to a hypothesized mean of 9. So we're going to put the hypothesized mean of 9 in there just real quick, just to kind of just to do it just one way, because there's two ways to do a confidence interval. But let's do it just one way. This is the familiar way. So we set it up. We got the test variable, terry cloth. We got the test value 9. And then what we're going to do now is we're finally going to click on that options tab. That is where you tell SPSS what is the confidence interval that you want it to calculate. So we want to go to that options. And it says right here very nicely, confidence interval percentage. What confidence interval percentage do you want? So make sure that you enter in the right percentage there. So in this case, we want to do a 95%. 95 is the default value. It's by far the most popular confidence interval. 95% confidence is tied directly into 5% in the tails, which is your alpha of 0.05. So anyways, we hit continue, we hit OK, and SPSS has calculated out our 95% confidence interval, importantly, of the difference. So you can see there in the one sample t-test, it's calculated out our 95% confidence interval for us. So let's do this one more time, because we were asked for a 95% confidence interval. We were also asked for an 80% confidence interval. So when you do those multiple confidence intervals, you can go straight into the one sample t-test, calculate it again, and all you need to do is go to options and change this to whatever confidence interval you want. So this time we want an 80% confidence interval. So we change that to 80. We hit continue. We hit OK. And we have 80% confidence interval of the difference right down here. And we're going to do this one more time. We're going to do it with 99%, because they also asked for a 99% confidence interval. So we go analyze, compare means, one sample t-test, go back to options, hit 99, hit continue, hit OK, and we have our 99% confidence interval as well. And that's as easy as it is. You can calculate any confidence interval all the way from, 0%, which would be your point estimate, all the way up to 99.999 as high as SPSS can go. All right, so let's take a look at what we actually have here. So we're going to take a look at the output. And I'm going to zoom in on the output. And as you can see, it's your old familiar output. We have our one sample statistics up here. We got our one sample test here. It's giving us that test value of 9. All right, so remember, we have that test value of 9, those 9 hours for our null hypothesis. And if we were going to calculate this by hand, what we could do is we could look up the t-statistic that we needed for a confidence interval. Which one is this, 95? We could look up the t-statistic that we needed for that 95% confidence interval. So we need that t-statistic, so we can look it up in our t-table, and then we could go to SPSS for the rest, right? So that estimated standard error is right there. So estimated standard error is at 1.73172, right? And then we also have the degrees of freedom to help us look up our t-statistic that we need. And we also have the, what do we need? We need that. And we also have our sample mean. All right, so the sample mean we have up there. But if we don't want to do that by hand, we can actually go here to this 95% confidence interval of the difference. And we use that to calculate our confidence interval. So what this is, it's a 95% confidence interval of the difference. And it is the confidence interval of exactly what it is saying. First off, it reminds you it's a 95% confidence interval. Very helpful. Make sure that you're looking at the right confidence interval. Secondly, it tells you where the center of your interval is. The center of your interval is that mean difference, that's 6.3. So we have our center of our interval, that's 6.3. But notice, this is the interval of the difference. Sorry, this is the mean difference. So this is not how long the terry cloth mother, the monkey spent with the terry cloth mother. This is how much longer did they spend with the terry cloth mother. Remember that, it's going to come back. So this is how much longer did they spend with the terry cloth mother. They spent 6.3 hours longer with the terry cloth mother. And then it gives us our 95% confidence interval, and it says the upper bound of our confidence interval is 10.29 hours with the terry cloth mother, and the lower bound of our interval is 2.31 hours less than with the terry cloth mother. So those, or sorry, 2.3 hours more with the terry cloth mother. That's the range for the difference. So that's the range for the difference, and we have this, and it's been done. But notice that that's not what they asked for. So our typical way of running this t-test is not actually what they asked for, because they don't want to know how many more hours did they spend with the terry cloth mother. They want to know how many hours did they spend with the terry cloth mother. So in order to get to that, we got to figure out what are these confidence intervals of. And this particular one is the difference between the actual population mean and our assumed null hypothesis of 9 hours. So what we're going to have to do, there's two ways to do this. Number one, we can use the lower and upper bounds and some logic and some math to get it to that confidence interval form, to get it to that sample mean plus or minus form. So what we got to do is we got to understand that this is the difference. This is the estimate of the difference between your test value, 9 hours, and your actual mean, 15.3. So your test value is 9, your actual mean is 15.3. That's where that 6.3 hour difference came. So what we need to do is we need to take that null hypothesis of 9 hours, and we need to add that back into the difference, right? We need to add that back in. So this 6.3 hours becomes 6.3 plus 9, that is 15.3 hours. This 2.3 hours becomes 11.3 hours. 2.3 plus 9, that's 11.3 hours. This 10.29 hours becomes 19 hours, right? And now this is not how much more time did they spend with the terry cloth mother. Now this is how much time did they spend with the terry cloth mother. So we pop that in. We now know that our point estimate for how much time did they spend with the terry cloth mother is 15.3. And then the last thing we need to do is we need to not report a range. We need to break this down into our estimate, which is going to be our point estimate plus or minus some amount. And the last thing we need to do is we need to figure out what is that plus or minus amount. And the way that you do this, and it will work every single time, there's a few ways to do this, but the way that I like to do it, you take your upper value and you subtract your middle value. And that will give you the difference every single time. So we go 19.29, that's your upper value, minus 15.3, that's your point estimate, and that is going to give you 3.99, and that is the width of your arms. That's that plus or minus. So it's 15.3 plus or minus 3.99. That is your confidence interval. And that's the way that people like it reported, right? Whenever you see Gallup polls, they'll always say things like, oh, well, the approval rating is 47 plus or minus 3%. That's the kind of format that that people like to deal with. So that's what we're going to be looking for, that format for your confidence interval. So that's one way of doing this. Another way of doing it, where you don't have to actually do all of this math. So this is one way of doing it. But another way of doing it, if you don't want to do all of that math, is to go back to SPSS and go back to your analysis. And when you go to analyze compare means one sample t-test, notice that we set our test value to 9. So we literally took that test value out. And then when we were doing the confidence interval, we added it back in. That's because we wanted to show this first time around to be as close as it was to the t-test, the t-hypothesis test. However, if your question is asking you, well, let's start off with the first way. If your question is asking you to estimate the difference, some questions will. If the question is, how much more time will they spend with the terry cloth mother? I want that estimate. Well, then you put in your test value of 9. But if the question is, how much of something, right? How much time do they spend with the terry cloth mother? Not how much more, but how much time. In that instance, you can take that test value and you can change it to 0. And then when you go to your options and you run your 95% confidence interval with the test value of 0, notice that now, and I don't got to zoom in on this, but notice that now your mean difference, 15.3, right? You can read it straight off of SPSS. Your lower bound, 11.31, boom, the lower bound that we found. Your upper bound, 19.29, boom, the upper bound that we found. You're still going to have to go upper minus middle to get this plus or minus 3.99, but this is a way to let SPSS do the calculation for you. Yep.
So you said with how much more time you keep it at 0, or you change it? No,
for how much more time, you keep it at 9. For how much time, you keep it at 0. So if they're asking for an amount, right? Then you compare it to 0. If they're asking for how much more, then you have to put in the null hypothesis. You have to put in the 9. So, for example, if they were asking, let's keep it at the monkey sanctuary. If they were asking something like, well, give me an estimate for how much heavier the infants are, now versus a month ago. That's a difference. They're asking you for a difference. So you would put in how much they weighed a month ago, and then you would run your t-test and do your confidence interval. On the other hand, if they just said, I want an estimate of how much they weigh now, I want a confidence interval of how much the monkeys weigh now, then they want an amount, not a difference. They want the actual amount. So when you're doing your homework, when you're calculating your confidence intervals, be very careful to read the language there and make that determination. Are they asking for a difference, or are they asking for an amount? And it'll be there in the language. They'll either say how much more, what was the increase, estimate the decrease, or they'll say how much was there, what was the value, how much of this actually is there. So be on the lookout for that when you're doing your homework. You're ready to do, after today, about a third of your homework, but we still have to go through the other 2 tests next time. Well, let's wrap up our first look at confidence intervals here with our final kind of analysis, just so that you can see kind of how these confidence intervals work. All right, so we have our point estimate of how long they spend with the terry cloth mother. And again, your point estimate, the center of your confidence interval is based on your sample mean. That's always your best guess, right? 15.3 hours was how long the monkey spent the sample with the terry cloth mother. If we're going to estimate the population with a point estimate, that's what it is. And that's always the center of your confidence intervals, right? That point estimate is the center of each of these confidence intervals. One of the people that worked at that monkey sanctuary wanted to be 95% sure that they got monkeys, they got surrogate mothers for every single monkey, right? So they wanted to be 95% sure. So this is the confidence interval that's 95% sure. And what they can do is they can say, all right, we're going to buy enough monkeys so that they can spend 19.29 hours with the terry cloth mother, and then we're going to buy enough surrogates for that. And then I'm going to be 95% sure that every monkey is going to have access, enough access to a terry cloth mother, right? That's what that estimate means. Somebody else might be more budget conscious, and they might say to you, well, you know what? I don't need to be 95% sure. I just need to be 80% sure. What's your 80% confidence interval? And you would say, all right, my 80% confidence interval is still centered on 15.3, but now it's 2.42. So now, instead of 19.3 hours, and instead of 11 whatever it was, something hours, now we're going to have, let me see, 12.8 hours, I believe, and we got 17.72 hours. All right, so now we have an upper limit of 17.72 hours. And they can say, I'm going to buy less terry cloth mothers because they only need to spend 17.72 hours. I'm 80% confident that this is high enough. So that would be for somebody with a more budget conscious kind of perspective. And notice the interval has shrunk, right? Not as confident, you got a smaller interval. But let's say that we got one last person on this board of directors, and they are very animal-minded. And they say, no. 80%, that is not confident enough. I don't want to take a 20% risk that we don't have enough surrogate mothers. And 95%, that's not confident enough either. I don't want to risk a 5% chance that some monkeys are going to be without their mothers. I got to be 99% sure. I got to go that high. So now the interval becomes much wider, and we won't do the bottom interval here. We'll do the top one. So now we have 15.3 plus or minus 5.81. It's going to be 21.11. Now they're going to buy enough surrogate mothers so that every monkey can spend 21 hours with a surrogate mother if they want to. Don't have to buy one for every monkey, right? We're not 24 hours, but they can spend 21 hours, and now you can be 99% sure that even if the actual population mean is out here, you've still got it covered. That's how an interval works. All right, my voice made it. Miracle. But anyway, so we are going to have a homework assignment. It's not done through MyLab. It's done through Canvas. It's a homework Excel sheet. You can access it at this point, but just be aware that we've covered 1/3 of it. We're going to be doing dependent means and independent means confidence intervals next time. But this was our intro to confidence intervals, and that is all that I wanted to cover for today. So if you want to start up on your homework, if you want to check out that single sample t-test, give it a shot. I'll be here until the end of class. Otherwise, if your ability to do stats is failing like my voice, feel free to call it an early day. And that is what I wanted to cover for today. Oh, and just while we're here, before we head on out, the homework assignment, this homework assignment number 13 for confidence intervals, will be uploaded through Canvas, but it is also, much like your other homework assignments, self-grading. So it looks like one of your exams, but it does have the green grading cells included. So feel free to try it as many times as you can before you submit it. I'm fully expecting to get hundreds on every single student. So if it doesn't, work out the first time you go through it, erase your answers, try it again, try it again. You can try it as many times as you like in order to get 100% on this assignment. All right.